Ladies and gents, welcome back for semester 2. As you know, we've got another examination at the end of this semester, paper 2. So what we're going to start looking at today is learning outcome 3, which is use Fourier series calculation technique as a means of analysing circuits involved in complex waveforms. Assessed in paper 2. We're going to study that over the 4 or 5 weeks, but I think this one took that long last year. But the other learning outcome, Laplace transforms, takes a bit longer to get those techniques. So some of the work towards this is something that we've already done with this build on. But the Laplace transform is new, and you've not been taught the maths hardly at all yet. So spend more time. So what we're going to have a look at is what complex waveforms are. We'll look at how we calculate current for a circuit supplied by a complex waveform. Next week we'll look at Fourier series calculations so that we can see where Fourier components for a complex waveform come from. And then probably the week after, maybe a bit into next week, we'll look at how resonance can cause issues when there's complex waveforms involved. We get resonance with not the fundamental, but one of the harmonic components of the complex waveform, where those harmonics are not desirable for you, not particularly want to have that harmonic interference. Okay? So that's where we're heading anyway. So, complex waveforms. As you'll see when we look at Fourier series next week, if you've got a repetitive complex waveform of a particular fundamental frequency, so anything that is cyclic and repeats every so many milliseconds or every so many seconds, complex waveform, it's made up of a fundamental or base frequency, the repetitions, but can be resolved into a sum of a number of sinusoidal waveforms having frequencies f, 2 times f, 3 times f, and so on. So the bottom frequency, the lowest one, is called the fundamental. 2 times f is called the second harmonic, 3 times f the third harmonic, and so it goes on. So these component parts are harmonics. Second harmonic's twice the frequency of the fundamental, third harmonic 3 times. Okay. Now, you'll have already come across this in your studies a few times. We can show that the equation of a sine wave is little v at time t, little v because we're talking about instantaneous voltage, okay, is equal to capital V, that's the amplitude of that waveform, the maximum value, times the sine of omega t. And throughout this learning outcome, we are going to be dealing with sine waves largely in that form, omega form, okay? Where you're interested in what the frequency is in hertz, we can use the fact that omega is equal to 2 pi times the frequency in hertz to find out what that is. So if given a frequency in hertz, you need to transfer it into omega form so that you can have that style of equation with sine wave. All happy with that so far? Yeah. Okay, so complex waveforms. General equation for a complex wave can be built from this. So we've got, if we look at that, an amplitude and a frequency of a sine wave, a second amplitude, 2 times the frequency, so that's the second harmonic, third harmonic, fourth harmonic, and so on. And then, if you have, what you can have also in a complex waveform there's a DC component that goes at the beginning. So there's a DC component. All that would do is move the whole waveform up or down the y-axis. Yep. So a DC component, fundamental frequency V1 sine omega t, second harmonic V2 sine 2 times omega t, third harmonic V3 sine 3 omega t. So each of the fundamentals, each of the harmonics are a multiple of the base frequency, and they also have their own amplitudes and can, in some cases, have phase shifts as well. Okay, so that can carry on for as long as necessary to resolve into any wave. Any repeating wave shape can be resolved into an infinite series. All right. So, if we look at one of the particular things of interest is a square wave and turning that into an infinite Fourier series. If we take the sine wave Vt equals 100 omega t, that's this one, and add it to 100 over 3 sine 3 omega t, its third harmonic. Add those two together, we get this waveform here. So that waveform is that fundamental third harmonic, because there's 3 times the frequency. Yeah, the fundamental has got a frequency of omega t, yeah, and that's got a frequency of 3 times omega t. Yeah. No. Well, if you look at the period of these waveforms, that one's 6 and a bit. Okay, to get the same on here, we have to go 1, 2, 3 waveforms. 1, 2, 3. Yeah. So you go on three waveforms in the same length of time as one, meaning that's the third harmonic. All right. Yeah. You all happy with that so far? No. What the frequency is how many waves there are a second, isn't it? But we've got frequency in omega t form, which is important for this topic. Okay. So you've got a frequency for your fundamental. Yeah. Whatever that is, 50 hertz on our mains. Okay. Then the second harmonic is twice that frequency. So in the same amount of time, you'll have 2 waveforms. This is a third harmonic, so in the same amount of time, you've got 3 waveforms. If you had a fifth harmonic, which we're now going to look at, you'll see there's 5 waveforms in the same amount of time. All right? So if we look at adding on a fifth harmonic with its own amplitude, okay, we end up with that waveform. And what we're doing here is actually getting closer and closer to a square wave. You're closer and closer. As we add, if we kept on adding more harmonics, dividing the amplitudes roughly by the harmonic number, it's not quite that, as you'll see when we look at the Fourier series, but it's close enough for us at the moment. So the next one would be 100 over 7 times 7 omega t, and 100 over 9 times 9 omega t, and so on. You'll gradually see it reduce this ripple on the top, okay, and turn it closer and closer to a sine wave, to a square wave, sorry, because a square wave is an infinite series of odd harmonics where the amplitude reduces by a factor of a harmonic number. Alright? So we can represent, or a square wave can be said to have these harmonics as part of it in terms of the Fourier series. Everybody happy with that so far? Crystal clear. So, calculations involving complex waveforms. When we have a complex alternating voltage wave applied to a single phase circuit that contains R, L and or C components, then the resultant current will also be complex and contain harmonics. Alright, so if you've got a complex voltage, you're going to have a complex current as well. Yeah. As stated before, the component parts of a complex wave can be considered to be quite separate. Therefore, each harmonic of the voltage wave will produce a current dependent on the impedance of the circuit it is feeding at that harmonic frequency. So what we can do is calculate the impedance at each harmonic frequency, find the current at each harmonic frequency, and add them over all together to have an expression for the overall current. Alright? So that's what we're going to do today, is have a look at the stages in doing that. Okay, so you can see where you build up an expression similar to that for the current in a circuit that voltage is connected to. So, example. We've got a voltage 240 sine 100 pi t, so that's the 40 sine 300 pi t, a third harmonic, because the frequency is 3 times, plus 30 sine 500 omega t, a fifth harmonic. And that voltage is being applied to a series RL circuit at 12 ohms resistance, 9.955 millihenries. We're going to calculate an expression for the complex current. Alright? So, first thing we're going to do is find the current due to the fundamental. So I've taken the fundamental voltage out, and we're going to consider that on its own. What do we need to do first? Modify that just a little bit from resistance, impedance. Right, we need to find Z1. Formula for it. Two components in series. R plus XL J ohms. Yeah, it's an addition of the resistance R and whatever the value of XL is according to that component. And we really should be saying that that is XL1, because that's going to change value at the other two frequencies. resistance will not change. That will stay the same. So how do we calculate XL? Yeah. Or 2 pi f is equal to, Jake? Omega. Yeah, so we can say it's omega 1 L in this case. Yeah. So that is 100 pi times 9.55 times 10 to the minus 3. We push the buttons on that, somebody, please. Three ohms. Picked them numbers well, didn't I? Huh? Therefore, Z1 is equal to 12 plus 3J ohms. Now, as we're going to use that in Ohm's law with the voltage to find the current, what would it be best to do with that? Yeah, convert it to polar form. Calculator in, please. No. Radians. Omega means radians. Yes, you have. Not in the last exam, no, but it's one you do. Maybe. No, I don't think so, though. I think it'll be omega. What we got then? What we got? Anyone push them buttons yet? Sure. 245. I thought you said 7. 12.37 ohms. Angle 0.245 radians. So now we can calculate I1. 240 angle 0, so it's got no phase shift, and 12.37 angle 0.245. You can't have degrees because you're working with omega to get your frequency. Right? So no. Won't work. Sorry. Anyone got me an answer for that yet? .35 amps minus 0.245 rads. Yeah? Okay, so that's the current being caused by the fundamental frequency of 100 pi t. Yeah. Right. I can't fit it on. You don't have to put rad on. If you leave degrees off, radians are presumed. Okay, so if you've got room, put rad to make sure you're confirming you know what you're doing. Okay, but I ain't got room there, so I'll left it off. You won't lose marks for leaving rad off, but you'll lose marks if you use degrees where you should have used radians and know it. Okay, and you lose marks if you leave the degree symbol off when it should be there. Okay. Leave it off. Right, so we've done the first, the fundamental. Now the third harmonic. So we've taken the third harmonic voltage, and we're going to calculate the current due to that. So we need to find Z3, which is R, plus XL3 ohms no, I'm calling it 3 because that's the third harmonic. Yeah. Omega 3 L, which is 300 pi times 9.55 times 10 to the minus 3. 5 minutes, finish it off. Right, what was XL3? Nine ohms. Therefore, Z3 is equal to R12 plus 9J ohms. And converted to polar. Yeah. 15 ohms, angle 0.64. Yep. Therefore, I3 is equal to 40 angle 0 divided by 15 angle 0.64 equals 2 2/3 amps angle 5. Yep. Okay, so that's the third harmonic current. Now go on and calculate that current due to the fifth harmonic using the same method. Yeah, go back. Can we leave it there then? All right now, yeah? I'll put it on the next one then. Right. Omega 5 times L, or XL5, is equal to 15 ohms. Correct. Yeah. Therefore, F5 is equal to 12 plus 15 J ohms. Converted to polar. 19.2 ohms. Angle. .92 radius. Yep. More to do with significant figures than decimal places. Yeah, about 3, sometimes 4. Judgment, you know. If you used what you're used, you'll not be far enough out to make any difference to the marks you get. Don't worry. Okay. I'll just go and buy what I've got on my work solution. All right. So then we find I5 by the 30 angle 0 over 19.2 angle 0.92, which is 1.56 angle 0.92. Yep. Okay. So now we've got 3 currents, one for each of the 3 frequencies that make up that complex waveform. Okay, so what we can do now is write an expression for the overall currents. This is the circuit complete again with the full voltage waveform. We can now write I at time t is equal to, and then we need the amplitude of the fundamental, which was 19.4 sine, open the brackets, that's the first term, that's the fundamental, so that's 100 pi t minus the angle associated. Close the brackets. Plus, I'm going to do mine on a new line because I ain't got much room. Amplitude of the third harmonic, 2.67 sine brackets 300 pi t minus the angle was 0.64. Close the brackets. And then plus amplitude of the third harmonic, sine 500 pi t minus, I'll use what we had on the board if you don't mind, yeah, 0.92 on the end of the units. So from that complex waveform of 3 components, a fundamental, third and fifth harmonics, we get an expression for the current that's got a fundamental, third harmonic, fifth harmonic. Yeah? All right? No dissenting voices? Right. What I've done is I've just popped onto my old friend Desmos and graphed those two waveforms. The green one is the applied voltage and the blue one is the current. If we zoom in a little bit, you can see that the overall current is out of phase slightly with the applied voltage overall. Maximum current is reaching 230 volts. Sorry, the maximum voltage 230 volts. Maximum current hits 18 amps overall. Yeah. Because at every point you're adding all three of those currents together. Yeah. All right. All happy with that? Yeah, and what I'll do is I'll take a screenshot of that in a minute and I'll put that into the whiteboard notes and put it on Brightspace so you've got that graph for reference to that problem. All right. So, going back to the notes that we've got an exercise for you to have a go through now. Complex waveform below, so you're given a complex voltage, it's got a fundamental frequency 100 pi t, a second harmonic at 200 pi t, and a third harmonic at 300 pi t. You're connecting it to a 15 ohm resistor, an inductor of 25 millihenries, and a capacitor of 1000 microfarads. All right. Initially, calculate the current due to the first harmonic, the fundamental. We'll check that one, and then you can go on and do the other two afterwards. Okay. So first calculate using similar methods. So this time we've got three components. Okay. Calculate the impedance. Find the current for the 110 sine 100 pi t part of the waveform. Right, let's just run through this fundamental so we make sure you're on the right wavelength and then carry on and finish it off. So, XL1, we need to calculate that. So that's omega 1 L, which is 100 pi times 25 times 10 to the minus 3 equals, what we got? 7.85 ohms. Yeah, and we need XC1, which is 1 over omega 1 C, 1 over 100 pi times 1000 times 10 to the minus 6. What did we get for that? 3.18 ohms. Alright, so then we can say Z1 is R plus XL1 minus XC1 J. $15 ohms plus 7.85 minus 3.18 J. Convert that to polar. What do we get? Yeah, Z1 in polar. 15.7. Angle minus 0.302 radians. Yeah. Therefore, I1 fundamental current is the 110 angle 0 over 15.7 angle minus 3.302 equals 7.01 amps angle hang on, this is not a negative angle, is it? I thought someone said negative, but never mind. Minus. We should know that's going to be positive because negative because the inductive reactance is bigger than the capacitive reactance at this frequency. So the overall inductive circuit means we get a lagging current. But how do we check that, guys? Remember? Inductive circuit, current lags voltage. Okay? So that's the answer for the fundamental voltage. Now go on and finish that off and calculate the second harmonic current and the third harmonic current and write an expression for the overall current at the end. So for the video, calculation of the second harmonic current, we find XL2 from omega 2 times L, be 15.7 ohms. We find the capacitive reactance at the second harmonic frequency, 1 over omega 2 times the capacitance, 1.59 ohms. Put that into the rectangular formula, 15 ohms plus brackets 15.7 minus 1.59 ohms. Convert that to polar, you get 20.6 angle 0.755 radians. Then use Ohm's law with the second harmonic voltage and the second harmonic impedance. Find the second harmonic current of 2.67 amps angle minus 0.755. And again, we've got an inductive reactance that's bigger than the capacitive reactance. So overall, the circuit is inductive at that frequency, and therefore the current is lagging the voltage. Yeah, and it's always a useful check that you haven't missed a negative sign off somewhere, got this calculations wrong. Just look at those two impedances and have that knowledge that if capacitive inductive reactance is bigger, the overall circuit's going to be inductive. If capacitive reactance is bigger, the overall circuit is going to be capacitive. And know what you expect in terms of a leading and lagging voltage or current. Alright? So, moving on to the third harmonic current, XL3 is omega 3L. That's 300 pi times 25 times 10 to the minus 3. We get 23.6 ohms. It's got bigger, and we'd expect that to get bigger because the frequency's going up. Yeah. XC3, 1 over omega 3 times C, 1 over 300 pi times 1,000 times 10 to the minus 6. And we get 1.06. That's what I got. Look, you're frowning, Seppi. What did you get? So, therefore, Z3 is equal to R, which is 15, plus the inductive reactance, 23.6, minus 1.06, close the brackets, J ohms. Converting that to polar, what do we get? I'll put 27.1 and 9 ohms, angle 0.983 radians. Yep. Therefore, I3 is equal to 25 angle 0 over 27.1 angle 0.983 equals 0.926 amps angle. Yeah. And again, inductive reactance is much bigger than capacitive reactance, so we've got a lagging current. Okay? You're frowning, Jasmine. You got it. Might be you used the different rounding on one figure or the other. If not, how far out are you? No. See if you can find it, because then you'll see how much difference it could make. All right. So make sure you have a look and see if you can find it. Okay. So therefore, overall current I at time t is equal to the current due to the fundamental 7.01, was it? Sine 100 pi t, and the angle was 0.3 minus 0.3 plus 2.67 sine 200 pi t minus plus whatever the last one was, 0.926 sine 300 pi t minus 0.983. Yeah. So that's how you would calculate an overall expression for a current, by calculating the expressions for each individual current due to each individual voltage that makes up the complex waveform. Alright, and again, if we graph that, you get something like that. The purple one is the voltage, and the black one is the current. And if we zoom in on that, we can see there's a phase shift between the voltage and current. Alright. And the overall current peaks or crosses this line after the voltage, so it's lagging, which we'd expect for a circuit that's inductive. Yeah. Okay.